All right, so the last topic we need to cover with solids and liquids is this concept of specific heat capacity. And before we talk about specific heat, let's just talk about energy more generally. Um, in chemistry, when we talk about energy, we're talking about this quantity, this sort of force that has the ability to either produce heat or to do work. And by work, we mean like the physics definition of work, where you're moving a certain mass over a certain distance. So these are two kind of very different manifestations of energy, but both of them are considered to be energy, and they're measured using the same units, which would be joules. That's typically what chemists and physics use. And then the biologists tend to use calories. I'm sure you've heard that word calorie before, because that's, of course, how we talk about how much energy is in food. A food calorie is actually a kilocalorie. So a food calorie is a kilocalorie, or 1,000 calories. Okay. And then we can convert between calories and joules using this definition here, where 1 calorie is equal to 4.184 joules. So just like with our other unit conversions, you could take that and create a conversion factor when you could have it that way, right? And that would help you convert from joules to calories, or you could flip it the other way. And that would allow you to convert from calories to joules, right? So just like all our other conversion factors, now we have this new one for energy. Okay, specific heat is defined as the amount of energy required to increase the temperature of 1 gram of a substance by 1 degree Celsius. Okay, so let's say I have a gram of water. How much energy is required to raise its temperature by 1 degree Celsius? And the reason why that's going to be a useful quantity is because then, let's say that I had 10 grams of water. Well, that will require just 10 times more energy. Or if I have 1 gram of water and I want to raise it by 10 degrees Celsius, that would again just be 10 times as much energy. So from this concept, we get this equation here, where our specific heat capacity, and this is going to be a number that we're going to look up for each substance. So water is going to have a specific heat, iron is going to have a specific heat, gold's going to have a specific heat, et cetera, et cetera. So specific heat capacity, which is again a number we're going to look up, times the mass times the change in temperature is going to be equal to Q, which is the amount of energy. Okay, so the M is mass, and delta T is the final temperature minus the initial temperature. Okay, so if I were to go from 15 to 20 degrees C, that would be a delta T of 20 minus 15 equals 5. Okay, be good about units. Right, so that's what that delta T is your final temperature minus the initial temperature. Okay, and then Q would be the amount of energy you need in order to accomplish that, in order to raise however much mass of a particular compound by that much, that change in temperature. Okay, and so, not unlike density, when we were talking about how, iron has a different density than water, has a different density than air, and you can kind of look that up from a table. We have the same thing with specific heat. Here we have our table of different specific heats. You see aluminum has a particular specific heat. We could look it up for iron, we could look it up for water, et cetera, et cetera. So once you know your material, you can figure out what the specific heat is based on this table here. Okay, and the units are joules per gram degree Celsius. And we'll talk about that, see why those are important here in a second. All right, so let's use this equation in a sample problem here. So we're going to find the amount of energy, and actually it wants it in kilojoules, so we'll have to keep that in mind. that's required to increase the temperature of 225 grams of water from 25.2 degrees Celsius to 90.5 degrees Celsius. Okay, so this orange term will give us our delta T. The mass is that 255 grams. And then the specific heat capacity is going to come from the fact that we're talking about water. So again, I'm going to go to my table here. I'm going to look up what the specific heat for water is, 4.184. So that's the value that I'm going to have to use in my equation. So 4.184 joules per gram degree Celsius times the mass, the 255 grams, times the delta T, which is, again, T final minus T initial is the delta T. So the final temperature is 90.5 minus 25.2 degrees Celsius. And this equation will tell us how much energy is required to raise 255 grams of water from 25.2 to 90.5, right? That's why we're doing the calculation. Okay, let me actually center this. Cool. So actually the first step we got to do is this step here. And that's because it could potentially limit our sig figs, right? So we have this mixture of addition and subtraction and multiplication and division. So we're going to have to pay attention to order of operations. As long as you do this one step first, figuring out this delta T first, then the normal rules for multiplication and division apply, and those are the easier rules. So yeah, trust me on this, you want to calculate the delta T first. So this would be 65.3 degrees Celsius. So now we just take the rest of our equation still. This hasn't changed any. Okay. All right. So now we're going to punch this into our calculator. 4.184 times 255 times 65.3. And we're going to get 69669.8. So right, first thing you're going to do is just throw down whatever your calculator gives you. Now we're going to go back and pay attention to units. This is where these compound units for the specific heat are important. We see that grams will cancel out and degrees Celsius will cancel out. So what we're left with is joules as the units for our answer. And that makes sense, right? Because Q is representing the amount of energy. So yeah, so we should get a unit that represents energy. So in this case, joules. Now it actually wanted it in kilojoules. So we're going to have to use our constants page. Whoops. Let's go to our course. Okay. And this table here, and remember how we read this table. This is telling us that 1 kilojoule is equal to 10 to the 3 joules. So in order to convert from kilojoules to joules, I have to use the fact that 10 to the 3 joules is equal to 1 kilojoule. Punch that into my calculator and I get 69.6698 joules. And then the last step is sig figs, right? So remember the rules for multiplication for sig figs. You're going to figure out how many sig figs each number has. I got 3 here, 3 here, and 4 in my specific heat. So that means my answer should have 3 sig figs. So my final answer here would be 69.7 kilojoules. Oh, sorry, yeah, kilojoules. That's my final answer. Okay, so it would take 69.7 kilojoules to heat 255 grams of water by 65.3 degrees Celsius, or from 25.2 to 90.5. One of the things I want to point out is that the sign in our answer, the fact that it's positive, tells us something about what's going on here. The positive I'll actually just, whoops, write it out. So positive Q means energy is being added to the system, which is in this case, this 255 grams of water. Okay, so when Q is positive, it means that you're putting energy in. You have to put energy in to raise the temperature. I could do the exact same problem, but kind of like reverse, where I'm figuring out how much energy for 255 grams of water going from 90.5 to 25.2, right? So going the opposite direction. Again, this is water, so it's the 4.184 joules per gram degrees Celsius times the 255 grams times the delta T, which is that now 25.2 minus 90.5 degrees Celsius, right? Because again, TF minus TI. So now I'm going from 90.5 to 25.2. So this means that my delta T is going to be negative 65.3. Okay. So now when I complete this problem, numerically, I'm going to get like, pretty much the exact same thing, except for it's going to be negative 69669 joules, rounded to the correct number of sig figs, negative 69700 joules, right? So negative Q means that energy is being removed from the system. All right, so the sign of Q, whether it's positive or negative, tells you about like the direction in which the energy is flowing. If Q is positive, that means that energy is flowing to your substance, which is raising the temperature. If Q is negative, it's the opposite. You're removing energy from your system, which is what's dropping the temperature. Okay, and the last problem I wanted to do is using the same equation, but see, in this problem, we were given the specific heat, or we could find it from our table. We were given the mass, and we were given the delta T, and we were trying to find Q. But just like any equation, I could, as long as I give you 3 variables, you can solve for the 4th. So if I gave you Q, specific heat and mass, you could solve for delta T. Or if I give you Q, specific heat and delta T, and delta T, you could solve for mass, right? So anytime there's one variable that's, you have the 3 variables and just one missing, you can always solve for that last one. So let's do this example here, and we're going to actually use the same amount that we found in our example problem. Okay, we're going to say we're going to put in this 69,700 joules of energy, but instead of being water, we're going to do it to iron. Okay, so our new question is, what would be the change in temperature if 69,700 joules of energy were added to 255 grams of iron? Right, so the amount of energy that we're putting in is the same, the mass is the same, amount of energy we're putting in now, and we have the mass. The difference is that now we have iron, and that's going to change our value for the specific heat. Okay, and notice that now the variable I'm solving for is going to be that delta T. Okay, so we can rearrange this equation here. I'm going to have to divide both sides by specific heat times M. Move this over. Divide by specific heat times M. And on my right-hand side, specific heat would cancel, mass would cancel. So I'm left with delta T, and that's exactly what we want, right? So when we rearrange, we get the delta T is equal to Q divided by specific heat times M. Okay, and again, the Q is given, that's that 69 700 joules. The mass is given, that's that 255. And the specific heat I'm going to find from the fact that I was told that it's iron. So we got to go back to our table and see that iron has a specific heat of 0.444 joules per gram degree Celsius. So plugging everything in, 69,700 joules over 0.444 joules per gram degree Celsius times 255 grams. That would tell me my delta T, right? So this will tell me how much temperature this 255 gram sample of iron is going to increase in temperature based on the input of 69,700 joules. So plug that into my calculator, see what comes out the other side. We get 615.615. Go back and look at units, right? So on the bottom, the grams cancel, and then I'm having joules and dividing by joules. So unit-wise, what I'm left with is 1 over degrees Celsius, and this is just equal to degrees Celsius. So, which is good. That's what I would expect for a change in temperature units, right? For that to be in Celsius. So my delta T is 615 degrees Celsius. Again, paying attention to sig figs, each one of these have 3. So really my final answer would be 615. Oh, no, it would not. Rounding correctly, it would be 616 degrees Celsius. That's my final answer here. And if we just compare that number to what we had in the previous example, right, the water raised in temperature by only 65.3 degrees Celsius. The amount of energy that was input was the same and the mass was the same. The only difference is that specific heat. So we had about like 10 times more, roughly 10 times more of an increase in temperature for iron. That's because the specific heat for water is about 10 times higher than that for iron. Right? So in gen, it's not quite, it's like 9 point something, but whatever, about 10, right? And so the bottom line is you have to put in 10 times more energy into water to raise the temperature by a single degree Celsius than you would iron. And that, you know, it might sound a little weird. Water is actually a surprisingly difficult substance to heat. It has a surprisingly high specific heat. And you guys probably actually already know this or have encountered it in your kitchen if you go to make pasta or rice or something like that where you're boiling water, right? You put this pot of water on the stove and the metal pot itself, the metal part, gets hot very quickly. And then you have to wait and wait and wait for the actual water to heat up inside, right? So this is just a reflection of these specific heats. In general, metals tend to have relatively low specific heats. You know, you see gold is incredibly easy to heat up. And then other substances like water have a much higher specific heat.